Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and on this channel we talk about all things Gen Chem related. On this video, I'll be covering formal charges and resonance structures and how you can distinguish between them. Let's get started. If you've been following along in series, you should have done the video that was before this where we covered a number of different examples of Lewis structures. And I kind of left you guys hanging when I talked about how to determine which structure is most stable or most preferred based on the different combinations that you're able to come up with. And so this video is going to help you to understand what those different structures really represent and be able to do a quick calculation to be able to determine which is the best or more preferred structure. And so something we can do when we're coming up with multiple structures is explore what is called the formal charge associated with the atoms that are present in that Lewis structure. And so remember, as we're creating these bonds, we're having some situations where we're sharing electrons between atoms, or even times where we're giving electrons from one to the other. And so this does result in atoms having what are called a formal charge. Now, these formal charges really are a great bookkeeping method that can be done to make sure that we're not violating anything when it comes to creating these more stable structures. So there is a very quick calculation that you do, and the formula is found for you here. And so for the formal charge of an atom, what you would have to do is take into consideration the valence electrons, how many are found in that atom. Then you subtract out the non-bonding electrons. And notice I'm saying electrons, not pairs. So the electrons on that atom that are not involved in bonding, minus half of the electrons that are involved in bonding electrons. Notice I'm not saying pairs. If you want to think about the bonding part as pairs instead, you have to take away that half. So you could also say this formula is formal charge is equal to the valence electrons minus the lone electrons, still not the pairs, minus the bonding pairs. And if you drop the half, then you can just count the pairs as is. Now, when we're dealing with formal charges, we would do this for every atom that's present, all right? And then overall, when we add them up, they should add up to the overall charge of the molecule. Or in the case where you're dealing with an ion, it would charge up to the overall sum of the ion. And so you can see in this example here for the oxygen on the left, which has 4 lone electrons, you end up with a valence charge of 0. Whereas the oxygen on the right, you end up with a a formal charge of -1. And that's because that now means that there's an extra electron that came from somewhere that is now present there. Okay. Now, when we're evaluating which structure will be more preferred, what we're going to keep in mind are these 3 simple rules. First, you're going to be looking for a structure that has the fewest number of formal charges present. So when you're dealing with multiple structures, multiple options, the one that has the fewer number of formal charges would be the more preferred structure. And the better structure will also have the smaller formal charges. So sometimes formal charges are inevitable, but you're going to be looking for the one that has the smaller number. So a 1 versus 2 or 2 versus 3, so smaller number. And then last but not least, and probably to me, one of the most important rules is that the better structure is going to have the negative formal charge, if one exists, must land on the more electronegative atom. And that's really going to help you to distinguish between some of these different options that you guys may come up with. Those structures that we're dealing with, these structures that seem to only differ by, a pair of electrons, whether they're as a pair or as a bond, are what we call resonance structures. So those resonance structures that we're creating we can try to distinguish between them by looking at these formal charges. And so we drew this before. You guys should remember seeing this slide. We worked on a few of these. And so shown here are some of the basic or initial forms of these compounds that we may have come up with. And so we can assign formal charges for the atoms that are found here. So let's go through a few. So if we look at the carbon dioxide, well, we would do a formal charge for carbon. Carbon would be 4 valence electrons minus 0 lone electrons. There's no lone electrons on it, minus half of the bonding electrons. So minus half of 8, or you could just simply write 4 for the bonding pairs. And that gets us a total of 0. Now for the formal charge of oxygen, And notice both oxygens have the same setup. They have the same number of bonding electrons and lone electrons connected to them. So we could do this calculation once and then adjust the number at the end. So for oxygen, the valence number is 6 minus 4 minus 1/2 of 4, or 2, which gives us also 0. And if I multiply this by 2, that also still gives me 0. And when I add those up, I get a total of 0, which does add up to the charge of the molecule. It's neutral, okay? And so that would be a good structure. Now in this SeOF2 example, we'll remember we had 2 different versions, and I'll quickly draw that second option for us here, where we ended up with a double bond instead of that lone pair. Okay, so we could do formal charge calculations for both of these molecules to figure out, well, which is the more stable of the two. And so let's start with the one on the left. So if we do a formal charge of selenium, that would be 6 for its valence electrons, minus 2 lone electrons that are on there, on just the selenium, minus half of the bonding electrons, or minus 6, and that gives us an answer of positive 1. For the fluorines, we would say 7 minus 6 minus half of 2, which would give us 0 times 2, still 0. And then formal charge for oxygen, well, that would be 6 valence electrons minus 6 minus 1/2 of 2, or minus 1, gives us negative 1. Now, overall, when we add these all together, we end up with a total of 0. So that checks out. The formal charges do add up to 0. But we want to be able to look at, do we have the most stable one? And so if we compare the formal charges that we see in this first molecule or option or resonance structure compared to the second, that will help us to figure out the more preferred version. And so in this case here, if we do a formal charge for selenium, we would now end up with 6 minus 2 minus 1/2 of 8, or 4, gives us 0. The fluorine doesn't change, so that's still 7 minus 6 minus 1/2 of 2, gives us 0. And for the formal charge of oxygen, that would give us 6 minus 4 minus 1/2 of 4, or 2, gives us 0. And if we add all that up, we get 0 as well. So which one would be better, right? I remember I left you guys hanging on the last video. Well, let's look at it. In the first example, we have multiple formal charges that are generated compared to the second one where we have none. We also have a situation where we have a negative formal charge, but it didn't end up on the most electronegative atom. It's actually on the oxygen rather than the fluorine that's present. And so because of this, the fact that the negative formal charge didn't end up on the most electronegative atom, the fact that there are more formal charges present, that tells us that in fact, this one would be the more stable one. Okay, so you'll want to be able to make those distinctions as you are walking through these. Okay, I'm going to erase some of this just so that you guys can see what I'm doing. So just if you missed some of that, make sure you guys rewind. Okay, so let me go ahead and erase some of that just to give us some more space to work through the remainder of these charges. Okay. All right. So if we look at the nitrite molecule, so formal charge of nitrogen, well, that would be 5 valence electrons minus 2 minus 1/2 of 6, which gives us 0. So that's good. Now, notice in this one, the 2 oxygens are not situated the same. They don't have the same bonding pattern. One has a single bond, one has a double bond. So when you're dealing with this, you have to actually do formal charges independently for those 2 oxygens, not like what we did with the fluorine on the previous example. So if we do the formal charge for the oxygen on the left with a double bond, we would say 6 minus 4 minus 1/2 of 4 gets us 0. Okay, so that's good. And then for the formal charge for the other oxygen on the right, we would say 6 minus 6 minus 1/2 of 2, or you could just simply say 1, and that gets us -1. Now, when we add that all up, we get -1. And remember, these formal charges should add up to the charge of the molecule. In this case, it's a negative, so we need a formal charge, right? And so then we also look and see, okay, is this negative number on the most electronegative atom? And indeed it is. And so in this case, this would be perfectly acceptable. If you came up with that second structure, remember I told you guys there was a second way you could draw this. The other option was that you could have put the double bond on the other side, like so. And in this case, when you compare the formal charges, you get the same exact pattern. So they're both equally comparable, okay? All right, again, I'm going to erase some space just so you all can see what we're doing here. So I'm going to go ahead and erase all of these so we can work on the other side. Again, I won't show all the options for you. You guys can work through the options and come up with the best. At the end, you'll get to see the final verdict on the most preferred structure for some of these things that have resonance structures that exist. So get all this out of the way, just so it's just cleaner for us to look at. All right, so look at H3PO4. Now remember, we did have a secondary version that had a double bond at top compared to this. So we'll do the formal charge count for this. I want you all to do the formal charge count for the one with the double bond option and make your determination, which is the preferred route, okay, or preferred structure. So if we do the formal charge for phosphorus here, well, that would be 5 minus 0 minus 1/2 of 8, or 4, gives us +1 for this structure. Again, our oxygens are not the same, so I'm going to need to do a count for the oxygens that have two bonds to them, and then one for the one that only has one single bond. So those are the 3. And so that would be 6 minus 4 minus 1/2 of 4 gives us 0. So that's good. And times that by 3 still equals 0. And then a formal charge for the oxygen on top, that would be 6 minus 6 minus 1/2 of 2 gives us -1. And then the formal charge for each hydrogen, again, they're the same bonding pattern, so we can do it once and then multiply at the end. So that would be 1 minus 0 minus 1/2 of 2, or -1 gives us 0. When we add all that up, we do end up with 0, so that's good. But we need to compare to that other version. Remember that other version, we instead had a double bond here, and so that was gone. And so that means our phosphorus and our oxygen formal charges would be impacted. And so do that calculation to determine which one would be the more stable. Remember, the one with the fewer number of formal charges would be preferred. The one where there's a negative that ends on the more electronegative atom is preferred. Okay, so just keep that in mind as you go through those options. Okay. All right, moving down to the next one. And remember, with this one, we showed this option, but we also had an option with a double bond. I'll just work through the calculations here, and you'll see at the end all of the answers. So we have the formal charge of sulfur in this case. So that would be 6 minus 2 minus 1/2 of 6 gives us +1. Now, each of my oxygens are the same. So formal charge of, I said 6 up here. That should have been just a sulfur. Formal charge of oxygen would be 6 minus 6 minus 1/2 of 2 gives us -1, excuse me. So if we have -1, but there's 3 of them, overall we get -3. -3 plus +1 gives me an overall -2 charge. So that does check out to what the charge of the molecule is. But again, explore the formal charges that you get with when you have double bonds present and figure out which is the more preferred structure. Okay. All right. And then last but not least, we'll tackle the bottom for the formal charge of phosphorus. I'm thinking phosphorus, but wrote 5. So phosphorus would have 5 valence electrons minus, again, focus on just 1, 2 lone, minus half of 6. All right, so that would give us 0 times 2 is still 0. And for the hydrogens, each of them are the same. So we would say 1 minus 0 minus half of 2 or minus 1 gives us 0 times 4. Overall still equals to 0. Okay. And so specifically for SeOF2, H3PO4, SO32 minus, you guys probably had some different options that you came up with, and NO2 minus. So look at those formal charges to determine which is the preferred resonance structure. Okay. So remember that bonding is occurring as we are trying to create less potential energy in, pause for a second. So go back and delete the transition here. All right. So again, these different types of structures that we're coming up with, those are what are known as resonance structures. So resonance structures are those that seem to only differ in the position of electrons and not necessarily the atoms that are present. So if you notice in those examples that we were doing, like the SeOF2 example, or even SO32 minus, the difference was that we weren't moving the actual atoms. We were just simply taking a pair of electrons and either having them situated as a lone pair or as a bonding pair. And so those are what we call resonance structures, things that differ by just that position of electrons. Now, it's important to remember that the actual molecule that exists is actually a combination of these different resonance structures that you come up with. It really exists as a hybrid between these, where that electron pair that looks like it's going in or out is actually kind of smeared against, kind of like how cream cheese is spread against a bagel. It's smeared all around the entire molecule rather than flipping back and forth, okay? And so we can use those resonance, we can look at those resonance structures and evaluate the stability of them based on those formal charges. So again, when you're dealing with creating resonance structures, you're simply changing where those electrons are positioned as either a lone pair or making additional bonding pairs. But the same rules are going to apply when we're evaluating how good a structure is. Remember, the sum of all the formal charges should add up to the overall charge of the molecule. The better structure will be one with the fewer number of formal charges. You'll also have the smaller formal charges present. And then again, that negative formal charge, if one exists, will end up on the more electronegative atom. And so you can see this when you're coming up with different resonance structures, how you can use the formal charges to help you identify what the best situation is. So your overall kind of cadence you should be doing is first draw your Lewis structure, then come up with the formal charges that are there, and then you move a pair of electrons to either create or take away a bond that's present. So either you're creating a bond or you're making a lone pair. And you always have to bear in mind if that element is one that can actually have more than 8 in it. In this case, if we were trying to make a pair here, if we were moving this pair down to make a bonding pair, well, that would make nitrogen have too many. And so we then have to take away a pair in order to maintain that octet. Okay, so keep in mind, if I make a bond, I got to break a bond somewhere, typically, especially if I'm dealing with something that can only have 8 around it. Okay, but in this case, when we look at the potential places that we could put that bond, that double bond that's occurring, each of these would actually end up being equivalent resonance structures based on their formal charge calculations. Okay, so again, big piece you want to remember, when we're evaluating these resonance structures, the better structure will have fewer formal charges, the better structure will have smaller formal charges, and the better structure will have a negative formal charge on the more electronegative atom. All right, and so if you were following along with some of the examples that we've done, we've seen these molecules shown for us, and a few of the formal charges are shown for us. When we explore the different options that are out there, the different types of resonance structures that we can come up with, we see that there are more preferred structures that exist over others. So in the case of SeOF2, the situation where you have that double bond present would be the more preferred structure, the more stable structure, because there are no formal charges generated in that manner. In NO2-, they're equivalent, right? Because they generate the same thing on opposite sides of the nitrogen. For the H3PO4 example, the version with the double bond is more stable. Again, you end up with no formal charges present compared to that negative and positive one that are present. When we're dealing with the SO3 2- example, having at least one double bond present is the preferred method. And you can see that double bond could be placed on the left, on the top, or on the right. Okay. Bear in mind, you could have made this with even more double bonds, right? Because sulfur can have more than 8, but you would see as you make more and more double bonds, you're going to add more and more formal charges to that molecule, making it less stable. Okay. And so that's the kind of distinction you want to be able to make as you're coming up with these structures. First, draw the structure, explore the formal charges that you come up with, and then pick out which would be the more stable. I hope this video helped you guys understand resonance structures and formal charges. Make sure you guys go back and try all these examples and let me know how they turn out for you. Make sure you guys like, comment, and subscribe, and let me know what other content you want to see. I'll see you guys in future videos. Have a great day.